Hello and welcome back to another 15-minute tutorial on chemistry the right way with me, Mr. Wright. And on today's 15-minute tutorial, what we're going to be talking about is ions, charges, and this really weird term called oxidation state, which so many chemistry students are like of the ages sort of struggle with this idea. They keep thinking it's a lot more complicated than it actually is. So let's go ahead and make sure we understand what we've got. So ions, as we learned in another video, or we learned in our coursework, are any species that contains a charge. So that is an overall, we call it a net charge, a species with a net charge. Now, they can either be positively charged or negatively charged. Now remember, ultimately, this positive and this negative just simply mean opposite of each other. There's no actual such thing as a positive charge and a negative charge. It's just a surplus of one or the other in the atom. If we have a positive charge, then what it means is we've got the positive center, that's called the nucleus of the atom, right? The nucleus and the number of electrons is a deficit of electrons, right? If we have a positive charge, that's an electron deficit. Don't worry about this one. And if we have a negative charge, we've got an electron surplus. But the nucleus remains the same throughout, okay? And if we have a positive ion, we call that a cation. And if we have a negative ion, we call that an anion. Okay? Anions and cations, but by how much? And that's where this Q net comes in, okay? Q net. Q is a symbol for just charge, and the net is just a simple difference between the number of protons in the nucleus and the number of electrons that are in orbit around or making up quote-unquote classical surface of the atom. Remember, atoms don't really have a surface. So, taking a look at that. Okay. We'll go back and we'll take a look at this. Now, it's important to know that some substances, some atoms, some atomic types have fixed net charges and some of them have variable. And I'm just going to cut to the chase. That number, that charge deficit or surplus, is what in chemistry, we just call it the oxidation state. It's an old name and it just comes from the idea of this is the effective charge that atoms or ions would take when they were combined with oxygen. I'll show you an example in just a moment, but let's just take a look. The surplus charge. So we've got P plus E neg equals Q net. This Q net is the oxidation state. It's just that simple. So if I have an atom with, I'm just looking at my periodic table, right? If I have an atom like manganese, Mn, right? It's got 25 protons in its nucleus. That can't change. If this number changes to 26, then it's no longer manganese, it's now iron. If it changes to 24, it's no longer manganese, it's chromium. This number, the number of protons, and this symbol, the actual sort of our symbol for the substance, they're fixed. Now we do have a little bit of variation on the top here in that nucleon number because we can change, and Mother Nature does that, right? It has a variable number of neutrons in the nucleus. And so we refer to each particular one as a nuclide. In this case, I'm going to go with a 55, right? So 55 over 25 Mn. Now, the reason I choose manganese is because manganese is a metal, the lead sort of element in a group of elements that have a tremendous number of various oxidation states. So this 25 right here is always going to be in here. Okay, it's always going to be there. So I'm always going to have 25p plus. Can't change that. But I can have various different amounts of E neg. I can have 23. And when that happens, 25 positives, 23 negatives, I've got an extra 2 positives remaining. So that would be Mn plus 2. Okay? That's its overall, you could call it an ionic charge if you really wanted to. I don't like to use those terms very much because ionic charges tend to lead students to think that everything just bonds ionically, and really don't, including an awful lot of metals actually bond covalently or in different ways. And then we can go on from there. We got manganese, you can have plus 2, you can have plus 3. So we drop this down again to 22, that'll give us a plus 3. So we've got Mn plus 3, right? 25 protons, 22 electrons. I got an Mn plus 4. Okay? So as you can see, I just keep lowering the number of electrons to keep that charge, that Q net, that oxidation state, ever increasing. 6 and 7. Mn plus 6 and Mn plus 7, right? And this one is really high oxidation state, right? Very, very high oxidation state represents the least number of electrons. So in order to get to a plus 7, right, I'm going to have 18 electrons, plus 7. Now, these numbers are important because they're what we call periodic numbers. We'll get to those in another vid, but take a look. These are all charge numbers, or they're all cation oxidation numbers. That's all that they are, right? They're just the charge number overall after the net imbalance. Now that's manganese. I chose manganese because it has a great deal of them. But then we can also have the reverse, right? We can have substances that, and I'll show you a little bit more complicated one, but let's talk about oxygen itself. So I said that the term oxidation state comes from the idea of what happens when compounds are formed between various different substances and oxygen. This is an old idea. So old, in fact, that not all of the elements actually on the periodic table were at that time discovered. So oxygen was once thought to be like the most reactive substance. Reactivity is an issue for a whole other day. It's very complicated, but it was determined that most things would oxidize because a lot of things do, because oxygen is really reactive and it's really abundant in our atmosphere. But for instance, our manganese, our iron, there's a great example, right? We all know that iron rusts. Iron rusts, or we say that iron oxidizes. So iron, Fe, will start out, I mean, you can actually polish it, it can actually take on a reasonably good shine, to be very honest with you, almost mirror-like, as it was done in the ancient world. It was once believed to be a very, very precious metal because it's difficult to extract. Iron can bond with oxygen freely from the atmosphere, and it can form a couple of different compounds, and one of them is that oxide of iron, and the other one is that oxide of iron. Now, the numbers on the bottom, these numbers represent just the ratio of atoms in that particular compound. So here, because we've got nothing written, there's a 1-to-1. So for every 1 atom of iron, there's 1 atom of oxygen. Here, for every 2 atoms of iron, there's 3 atoms of oxygen. But it's a little more complicated than that, because the only way they stick together is by being ions. In this example right here, what we can say is this. Oxygen, 99% of the time, is going to have an oxidation state, and it's going to be anionic. That means negatively charged. Positives, in a chemical formulae, right, we write positives before negatives. Just like in a number line, okay? Positives before negatives. It's just what we all agree to do. And so we write, another way of saying this is we write cations before anions. Okay? Oxygen, in its normal anionic state, simply takes a -2 charge. And it takes a -2 charge over here as well. But now what we've got is what is the cationic charge on my ion? Okay? Or what is the oxidation state? These numbers underneath represent that iron has different possible oxidation states. But there's a really, really simple trick here. If the numbers on the bottom are the same, like they are here, 1 and 1, I know we haven't written them in, we don't write in 1s, right? We just don't write them in. And the reason we don't write them in is the same reason we don't write 1x, we just write x. Okay? It's just algebraic. So, if these lower numbers, or our ratio numbers, are the same, then the oxidation numbers are the same, but opposite. Opposites attract, like things repel. -2, +2. So we have an Fe of +2, and over here, the numbers aren't the same. So the trick that we use is to crisscross, okay? 2 and 2, 3, +3. So here we have an ion at +3. Now this is really, really simple. I have 2 atoms at +3. 2 times +3 is +6, right? 2 times +3 equals +6. 3 multiplied by -2 equals -6. Add them together, I get a neutral compound. 1 times +2, +2, 1 times -2, -2, add them together, neutral compound. So I've got 2 different oxidation states for iron. Iron can take a +2 commonly, or a +3 commonly. And this is what we refer to in compounds as an iron 2 compound or an iron 3 compound. Last bit on oxidation states is certain elements on the periodic table take sort of almost dedicated oxidation states. Now, there's a lot wrong with oxidation states in a very real sense, right? What we're trying to do is we're trying to just get an image, a picture, a rough sketch of what's going on with atoms, because atoms, some like to be positive, some like to be negative, and that's how they all sort of stick together. But it's a little more nuanced than that in actual reality. We discovered that thanks to, again, the science of quantum mechanics and what sort of went on from there. But don't get too far down that rabbit hole. So, the good news is we have these groups on the periodic table, right? So, periodic table, simple sketch, right? And then a bit underneath in your typical, what we call short form periodic table. So I've got group 1, group 2, etc., etc. Okay. These guys at the very end, we call them the noble gases. Their preferred oxidation state is 0. Right? And that means that they don't like to change their electrons in any way, shape or form. They don't like to give, they don't like to receive, they're on their own, that's it. Up here, group 1, the first group, these all like to take +1. That means they like to give away 1 outer electron. And in fact, most of them will only ever do just simply that. Just a +1. There's a little exception with hydrogen at the very top. Group 2 only like to go to an oxidation state of +2. Okay, that means they just give up their 2 outermost or valence electrons and that's it. The bit in between, the bit in between are the transition metals, which, by the way, the bit underneath the periodic table, called the F block in chemistry, is actually a part of. But the transition metals take variable oxidation states. So they can take, as in the case of manganese, they commonly will take a +2, commonly, but then they can have all kinds of different oxidation states. Some atoms will have 4 different oxidation states, some will only have 2, but they typically have a choice. So it's a little bit difficult, but just know that you're commonly going to find things that can go to a +2. Then it gets a little more complicated. I'm going to work backwards, right? So this is actually called group 17. The noble gases, by the way, in the very end with helium on the top, that's group 18 that goes to 0. Group 17, the halogens, typically like to go to a -1. Then the chalcogens with oxygen on top, that's group 16, typically like to go to a -2. But then it gets sort of complicated. I'd like to say that the pnictogens, that's the group with group 15 with nitrogen on top, they like to go to a -3. But we have a problem. And the problem is this, is that we actually have got right, however it goes on this periodic table. What we've got here is some are metals and some are non-metals. Non-metals typically like to form anions. All right, those are the negative charge. And then our metals typically like to form cations. As a rule, actually, metals can only form cations, but it's chemistry, so all rules can be broken, and I know of at least 2 examples of metals that take an anionic charge, but it's probably under like extreme cases. But anyway, the rule of thumb basically is it's hard and fast, or more hard and fast on the outside, and as you work your way in, it gets more complicated. Anyway, I hope that explains a little bit about oxidation states. Oxidation states, just that net charge, which is the imbalance between the number of electrons that are in orbit around the atom and the positive center. Remember, you can't change the positive center. Chemistry is all about manipulating those electrons on the outer side. Don't get too bogged down. If you like the video, go ahead and click the like. If you subscribe, you'll get all the updated content. And if you want to leave a comment or ask for a video on a new subject, more than willing to help out. Keep it going, keep studying chemistry. It's the best science that there is. All right, thanks, bye.